There are many ways to extract energy from water, whether it be a water wheel or a more optimised turbine, but I've never seen someone try to run an air-powered engine using water. Well, ignoring steam engines. This video is sponsored by NordVPN. More on them later. Without the use of Coca Mentos, we can increase air pressure inside of a tank using a pump to push more and more air into a fixed volume. Or we can use a fixed amount of air and reduce the volume of the tank. An easy way to shrink the volume of air in a tank is by filling the tank with water. But one small problem is the water must be at the same pressure as the air, or the air will just push it out. However, because water is roughly 830 times denser than air, we can use this to our advantage. If you swam down to the bottom of a pool, you'll probably have felt the water pressure on your ears, and no matter how large or small the pool was, you'll feel the same pressure at the same depth. This is because the static pressure of water is only relative to the depth, and is essentially the weight of water above you pushing down. And I plan to use this to create water pressure in my tank. The plan is to put a tank of water in the loft of my house, then run a tube downstairs to my tank full of air. The vertical distance between these tanks is about 6.14 meters, which means in theory, when I let the water flow down the pipe, the tank at the bottom should experience the pressure of being 6.14 meters underwater, which, when we calculate the density of water multiplied by the acceleration due to gravity and the depth, we should get around 0.6 bar or 8.7 psi of pressure. Then we can use this pressurized air to hopefully spin an air-powered engine. Or is it now water-powered? So let's build this tank. I could have opted for an easy choice of using a plastic drinks bottle, as these are very cheap and easy to source, and they can hold a lot of air pressure. But I want something a bit more fancy made out of clear acrylic. But as I've never made an acrylic pressure chamber before, I need to do some calculations. For example, a 150mm acrylic tube will require 2 plates on the end to hold the air inside. And at just 0.6 bar, the force pushing out on these 2 end plates is about 1060 newtons, or equivalent to supporting a 108 kilogram weight. So I used Fusion 360 CAD software to design the acrylic pressure chamber, and I chose to use 15mm thick sheets as the end plates. After running a pressure simulation, the thick end plates were probably a bit overkill, but it allows me to cut this lip all the way round to give more surface area for gluing. I've only ever cut plastic on my CNC router once before, and it was the clear perspex type stuff you can buy at local stores for shed windows. And I'm not sure if it was my cutting settings or the melting temperature of the plastic, but it was a nightmare to cut. So I crossed my fingers and attempted the acrylic lid. Which, to my surprise, cut really easily. Once finished, it perfectly fit inside of the tube, and it was now time to drill some holes and thread tap them for later adding some pneumatic fittings. I then sanded down the gluing area on the tube and began mixing some epoxy resin, which probably isn't the best glue option for acrylic, but it's what I had laying around and it's pretty strong. I also made sure to use plenty of it to fill all the gaps between the inner wall of the tube and the lip of the lid, which got a bit messy but worked well in the end. Then we can fit a tube inlet on the bottom and a 3D printed stand to give enough clearance from the ground. And on the top lid I can fit a pressure gauge and another tube outlet for the air supply to the engine. The next step is to run a long tube all the way from the ground floor up 6 meters into my loft, where I'll mount the water tank. Okay, this is the first pressure test. I've got 5 litres of water here, and the container with the tube running downstairs. I'm going to prop my phone up. The problem also is that I can't see if there's any leaks downstairs until I go downstairs. So I'm just going to have to hope that this doesn't leak. Let's start pouring. Water's running down. Let's hope I don't just find a massive puddle downstairs. So whilst we wait for the water to drain down, let me tell you about the sponsor of this video, NordVPN. A VPN is great for internet security and privacy, as it can hide your IP address, as well as encrypt your data. But NordVPN is more than just a VPN, as they now offer threat protection, which will guard your device from malicious websites, malware and trackers, even if you're not connected to a VPN. But if you do want to use it as a VPN, check out how easy this is to use. Let's say for example I want to watch Shawshank Redemption on Netflix. Unfortunately it doesn't exist here on the UK Netflix, but I can simply open up NordVPN, scroll over to the United States, click here, quick connect, and as you can see it's there at the top. Click it, click play, and you can watch the whole movie in full HD due to their high-speed connection. For the price of a coffee, the advantages that NordVPN gives you is an amazing deal. And for a limited time only, viewers of this channel can sign up for 2 years and get an extra month for free by clicking the link in the description down below. Plus, NordVPN offers a 30-day money-back guarantee, so why not give it a go?
Still going down. I might need to go check out what's going on downstairs. This is making me a bit nervous. Let's go check out what's happening downstairs. Please don't be a leak, please don't be a leak. Oh no, hang on. Hang on. There's no leaks. And we've got 0.5 bar. Ooh, right. I suppose I should go back upstairs and keep pouring. Nice. I think that might be it. The water level seems to be staying still now, so let's go check what the pressure is downstairs.
The pressure downstairs was about 0.57 bar, or about 8.3 psi, which is very close to the 0.6 bar that I originally calculated. But is this really enough pressure to run an air-powered engine? Well, if you haven't seen my air-powered engine videos before, then you'll have no idea what I'm talking about. So let's have a quick recap. In November of 2017, I 3D printed my first air engine that was based off the old Airhogs engines. And although it did run, it was extremely inefficient. So in April of 2018, I built a new engine that used a square piston and a cam and pushrod design, which was more reliable than my first engine, but still quite inefficient, as it was very difficult to seal the piston to the cylinder without lots of friction. Then 2.5 years later, in November of 2020, I came up with a completely new design that removed the need for an airtight piston by using a diaphragm and a new inlet valve that removed the need for any pushrod valves. And after refining the design way too many times, it outperformed the previous best air engine by a factor of 5. And could also run at pressures as low as 0.7 bar, or about 10 psi. But will it work with my new pressure tank? Not quite. And this reveals a problem that I hadn't previously considered. Not only do I need an engine to work at 0.6 bar, but I also need to consider the flow rate of the water into the tank. If I release all of the pressurized air, the tank takes about 1 minute and 20 seconds to fill back up to full pressure again. And it's too late to increase the diameter of the tubing, as that would require new holes to be drilled for larger fittings. So although I'd hoped that the engine would run at 0.6 bar, which is not that much lower than the 0.7 bar that it had previously worked at, in reality it needs to run at much lower pressure. So the first modification I made was to increase the diameter of the diaphragm within the engine, as this will increase the area that the air can push against, hopefully allowing lower pressures to apply more force to the piston. And to my surprise, it actually worked really well. At least down to about 0.3 bar, when the engine would stop and I would have to wait for the pressure to build back up again. The obvious next step would be to build an engine with an even larger diaphragm to run at lower pressure. But there's a small problem, because the design of the cylinder requires this cone section to allow for the diaphragm to expand. It means the piston has very little support when it reaches the top of the stroke. And making the diaphragm larger would mean increasing the unsupported distance for the piston, which means the piston needs to be longer and so does the cylinder, which will probably just increase friction. Also, the crankcase and crankshaft needs to be longer to avoid the propeller from hitting the cylinder. So instead of completely redesigning the engine, I decided to try tweaking a few things on the current engine. The first being the ball valve that lets the air into the engine. When 3D printing the cylinder head, the printer often leaves small blobs of plastic as it moves on to the next layer, and this means the O-ring used to seal the ball valve doesn't fit perfectly, which isn't an issue at much higher pressures that I normally run the engines at, due to the extra force pushing the O-ring into any small gaps. But at these lower pressures, if the ball doesn't perfectly sit on the O-ring, it will leak enough air to drop the pressure in the tank by almost half a bar. To fix this, I used my soldering heat gun to soften the plastic inside of the cylinder head, and then pushed the O-ring and ball into position to mould the plastic around it, which achieved a much better seal. I then made sure everything in the engine was running as smooth as possible, by sanding down any tight spots in the cylinder and aligning the diaphragm as best as I could, and the engine now sounds much smoother. But it's spinning way faster than it needs to be and running out of air. So I took the piston out and shortened the small pin that opens the inlet valve, which will hopefully reduce the amount of air that enters the engine per rotation. Almost like lowering the throttle. This reduced the pressure at a much slower rate, and the tank started to hold a constant pressure at just over 0.4 bar, which made me incredibly excited.
No! Don't stop! I thought we had a continuously running one then.
So I emptied the tank, carried the water back upstairs, and crossed my fingers for another run.
No!
I then realised that clicking noise you can hear was actually a huge amount of play in the crankshaft, which I think throws the piston off centre when it's unsupported by the cylinder. So I removed this play with a small spacer, mounted the engine on a solid stand, and attempted another full tank run. The engine was off to a smooth start and took around 50 seconds to stabilise the tank pressure at around 0.45 bar. Then at about 2 minutes and 10 seconds into the run, the engine suddenly dropped in RPM as the pressure reduced. But somehow the lower RPM allowed the tank to fill back up to pressure and the engine RPM increased again. Then at 3 minutes and 30 seconds into the run, the engine nearly came to a complete stop multiple times before switching direction. Which again allowed the pressure in the tank to rise. At this point there is so little air left in the tank that each breath of air that the engine takes will reduce the pressure by a huge amount, so it struggles to keep the pressure constant. And as the water reached the top of the tank, I cut it off early to prevent the engine from drowning itself.
We did it! We actually did it! Oh no, don't get water in the engine. Or the... Yeah!
I can't believe that actually worked. Not only was that the lowest pressure any of my engines have run at, but it was also the longest runtime I've ever had out of an engine with such a small amount of air, with a total runtime of 4 minutes and 42 seconds, running just on the pressure created from a water tank in my roof. I hope you found this interesting, and I'll see you in the next one. Thanks for watching.